Okay, so let's get started. So everybody can see the shared screen. Today we're going to discuss lecture number 3, which is hydration. Okay, so in the last 2 lectures, we discussed the historical concrete and also the manufacturing process of modern Portland cement. And today we talk about hydration, which is the chemical reaction between the water and the clinker. Okay. Right. So this slide is coming from last time, showing us the typical constituent materials or the oxide in Portland cement. Okay. So here shows the oxide, the major oxide, such as lime, silica, alumina, ferric oxide, and some other minor minerals. Okay. Remember the shorthand. C is for calcium oxide, S is for silica oxide. Okay. The major compound, by the way, is a combination of 2 or more type of oxide. Okay. For example, tricalcium silicate is 3 parts of calcium oxide with 1 part of silica oxide. And the shorthand is C3S. Okay. And we also have C2S, which is dicalcium silicate, C3A, tricalcium aluminate, and C4AF, which is tetracalcium aluminate ferrite. Okay. Tetra means we have 4 parts of calcium oxide with 1 part of alumina oxide and ferric oxide. Okay. The weight percentage here is not fixed. So depending on the type of cement, we could have more or less depending on the situation. Okay. And don't forget, we need some gypsum to control the hydration speed, especially for C3A. Okay. We're going to talk about hydration equations for these major compounds. And here shows the typical cement particle size. Okay. As we can see, for 50%, the medium size is around 10 micrometer. μm is for micrometer. Okay. So there are 5 major types of cement depending on the type of application. Okay. So here is a short video about these 5 types of cement.
There are 5 types of Portland cement produced in mills like you see here. These different types of Portland cement can be used to suit various design and construction needs. Almost all uses of concrete can be made with type 1. A general all-purpose cement suitable for buildings, bridges, floors, pavements, and precast structures. But some concrete structures require special needs. These precast pipes are exposed to sulfates in the ground. A type 2 cement gives the concrete moderate resistance to sulfate attack. The concrete for this winter placement will set and harden slower. A type 3 cement can be used to give higher strength concrete at an earlier age than type 1. Its application is similar to using a type 1 with a chemical accelerating admixture. The concrete for this dam will generate a tremendous amount of heat during hydration using a type 1 cement. A type 4 cement minimizes the heat for these massive structures. This sewage treatment plant is exposed to high concentrations of sulfates. A type 5 cement gives the concrete protection against these sulfates.
All right. Again, there are 5 major types of cement.
Portland cement produced in mills like you see here. These different types of Portland cement can...
Right. So type 1 cement is called normal Portland cement. For most general type of application, we can use type 1 cement. Okay. For type 2 and type 5, it is called moderate sulfate resistant cement, and type 5 is called sulfate resistant cement. Okay, sulfate resistance means that type of cement, type 2 and type 5, can kind of resistant to a type of chemical attack called sulfate attack. Okay, we'll talk about sulfate attack in future lectures. Okay, but the sulfate will coming from outside the environment, such as soil. If the concrete will be in touch with underground soil, okay, can also coming from underground water. Okay, so if the concrete is needed for sulfate resistance, we can use type 2 and type 5 cement. Okay, so for type 2 cement, we should limit amount of C3A to less than 8%. And for type 5, we need to further reduce amount of C3A to less than 5%. Okay, so the reason for that is because the second note here, the hydration product of C3A, which we'll discuss in a moment, may react with the sulfate, which is coming from the soil and underground water, and could cause expansion. They will generate a chemical called ethylene dye. So ethylene dye will expand, may cause the concrete to crack. Okay. Some of type 2 cement has low heat options. So if that's the case, we should limit the amount of C3S and C3A to less than 58%. Okay. Type 3 cement is called high early strength cement. Okay. So we should limit the amount of C3A to 15% or less. And type 4 cement is called low heat cement. Okay. We use low heat cement if we do not want the temperature of the concrete to be too high in situations such as big dam or mass concrete pouring. Okay. So for low heat option, we need to limit the amount of C3S and C3A to a certain percentage, as you can see from here, and also increase amount of C2S to more than 40%. Okay, the reason is because the nodes, the first nodes here, the rate of hydration or the how fast the compound will react with water is ranked as follows. So C3A will be larger than C3S, which is more than C4AF, and C2S is least amount of heat will be generated. Okay, so that's the reason for low heat option type 4 cement, we should limit the amount of C3S and C3A because C3A and C3S will generate more heat per unit mass. Okay. Okay, so here shows the typical application for type 1 cement. We can use for almost all type of applications such as Portland cement, pavement, slab on grade, reinforced concrete bridge, and reinforced concrete buildings. For type 2 and type 5 cement, okay, so this is again sulfate resistant cement. When the concrete will be exposed to underground, for example, this underground pipe or a slab on grade, if the soil has certain amount of sulfate, we may consider use type 2 and type 5 cement. Yeah. For type 3 cement is high early strength cement. So this type of cement will generate more heat. Okay. So the temperature in the concrete will be kept higher compared to, for example, type 1 cement. Okay. So for situations such as winter construction, we do not want the concrete to freeze. We're going to talk about the reason why. But to keep the concrete temperature high, we can use type 3 cement in winter construction to keep the temperature high enough. Okay. Here shows the emergency repair. or fast track paving. So we can use higher strength cement so we can increase the construction speed, and we can reopen the road faster, to reduce the traffic congestion. And the picture on the lower right showing us precast concrete members. Okay, so precast concrete members is like Lego pieces. We make these precast pieces in precast plant, and we ship these pieces to the job site, and we can combine these pieces together on job site. The reason for that is we can accelerate the construction speed. Typically, the concrete need 5 to 7 days before it achieves the strength. But because we use precast concrete, so that time can be moved to the precast plant. So on the job site, we only need to assemble the pieces together. The reason we use type 3 cement in precast member is because that will increase the turnaround time. Okay. For a certain time, we can make more pieces, okay, because the concrete can achieve its design strength faster. Okay. So this is some of the applications we can use type 3 cement. For type 4 cement, this is called moderate and low heat cement. We typically use in mass pouring, such as this big pier and huge dams here. Right. The reason for that, I'm going to draw some figures here to showing us why we need to use type 4 cement in these situations. Okay. The chemical reaction, the hydration will cause heat. Okay. So this is big pouring of concrete. Okay. And the dimension is, let's see, 100 feet. All right. Okay. So because the heat will generated during the hydration process, inside the concrete, the temperature could be very high. So sometimes it's close to the boiling temperature of water. Let's say the inside temperature is 90 degrees. But outside, it is close to the temperature of the air. Okay. So we have temperature gradient between the inside and outside. Okay. So that will cause outside concrete to shrink, but inside to expand. Okay. And because concrete is very brittle, and that difference in expansion and shrinkage will cause a so-called tensile stress. If the tensile stress of concrete is larger than tensile strength, the concrete will crack. Okay. By using type 4 cement, we can reduce the temperature inside the concrete. So reduce the tensile stress, so make the concrete less likely to crack. All right. So that is type 4 cement. The cement hydration, or the chemical reaction between water and cement compounds such as C3S and C2S, it will generate a lot of heat. Okay, so water plus cement, this chemical reaction will generate a lot of heat. The cement grain will, let's see here, dissolve, diffuse, and precipitate. So remember these three words, and we'll discuss this process in a moment. Okay. Again, the reaction is exothermic, which means a lot of heat will be released. Okay. The heat signature can be important to characterize the material development. Okay. Let's look at the chemical reaction for area of these four major compounds. Okay. C3S, C2S, C3A, and C4AF. Okay. So let's look at C3S and C2S first. Both of these two compounds will react with water and generate the same hydration product. One is called calcium silicate hydrate, or CSH. Okay. The number underneath the C and S and H could be different. Okay. Does not necessarily to be 3, 2, and 3 as we see from here. CSH is the major strength contributor to the strength of concrete. So that's the best hydration product for cement. The second hydration product is called CH. Okay. If you remember the shorthand, this is actually calcium hydroxide. So calcium hydroxide can be dissolved in water. So if the water passing by the concrete, calcium hydroxide could be leached out from concrete. Okay. So again, both C3S and C2S will generate CSH and calcium hydroxide, but the reaction speed of these two are different. C3S is faster, C2S is slower. That's the reason why for type 4 cement, the low heat cement, we need to increase the amount of C2S because the reaction is slower, and the reduced amount of C3S because C3S will generate a lot of heat. If you want type 4 or low heat cement, we need to increase C2S and reduce C3S. Okay. The next is tricalcium aluminates, C3A. The chemical reaction of C3A is pretty complicated. Okay. So C3A will react with water together with gypsum. Okay. And we have hydration product called ethylene. Okay. Depending on the relative ratio of C3A and gypsum, we could have another hydration product called monosulfide aluminate, or AFM. Okay, so this is ethylene AFT. This is monosulfide aluminate, AFM. Again, depending on the ratio of C3A and the gypsum. Okay. Remember, for type 4, type 2, and type 5 cement, okay, they are called sulfate-resistant cement. And for this cement, we need to limit the amount of C3A to certain percentage. Okay. The reason is here. AFM, which is monosulfide aluminate, one of the potential hydration product of C3A, may react with the gypsum here. That gypsum may come in from the soil or underground water. Okay, so after concrete hardens, AFM, if there's any left in the concrete, may react with gypsum from the environment plus water. It will form AFT, or ethylene again. Okay, so this chemical reaction will cause expansion or volume increase in the concrete. And because concrete is very brittle and very weak under tension, so that will make concrete crack if this happens after concrete hardens. Okay, so that's one of the reasons for sulfate attack. Okay, so C3A, the reaction is pretty complicated. Depending on the ratio of gypsum and C3A, we may have AFT or AFM, and it may cause sulfate attack. Okay. Next lecture, we'll look at in details of this hydration product. what is C3S looks like, what is calcium hydroxide looks like, ethylene guide, and monosulfide aluminate, and how they will affect mechanical property as well as durability of concrete. Okay, so today we only look at the chemical reaction between the cement compound and water. All right, so EFT is called ethylene guide. Okay, EFM is called monosulfide aluminate. So let's spend a little bit of time talking about why we give this chemical this name. Okay. For ethylene guide, we can rewrite ethylene guide as this: 1 part of C3A with 3 part of gypsum plus 32 part of water. Okay, so A is for alumina and F is for ferric. Okay, T actually is short for tri or 3. Okay, so that basically tells us for 1 part of C3A, sometimes we have alumina, ferric to interchange with C3A. We have 3 part of gypsum or 3 part of sulfate involved with it. So that's the name AFT coming from. For monosulfide aluminate or AFM, we can rewrite its chemical reaction as 1 part of C3A with 1 part of gypsum with 12 part of water. So that means for every part of alumina or ferrite, we have M is for mono. Mono means that's only 1. Okay, so every part of C3A, we have only 1 part of sulfate or gypsum. Okay, so that's the name AFM coming from. Okay, both AFT and AFM are well crystallized materials, but the strength of these two are much weaker compared to CSH. All right. So let's continue. This is the first major compound, C4AF. The chemical reaction of C4AF is pretty similar to C3A. Okay. But the difference between C4AF and C3A is it may not cause troubles as C3A because there's no ethylene guide formation as in the case of C3A. So that means C4AF will not cause cracking due to sulfate attack. So better sulfate resistance for C4AF. The reaction speed of C4AF is also slower than C3A. This is another good thing. Okay, and ferric F play the same role as A or alumina. So F and A are interchangeably. Okay. So for example, you can think this part C6AF with 3 parts of sulfate and H32 as the equilibrium of ethylene guide. Okay, but reaction speed is slower than aluminum phase. And this part you can think as monosulfide aluminate, but with slower hydration speed. Okay. All right, here's more details about the hydration product. Again, next lecture we'll discuss in more details. The most important hydration product is CSH. Okay, you can write CSH or C-SSH. Sometimes we also call that CSH gel. Okay, we call that gel because it is not well-defined crystalline materials. Okay, CSH is similar to topomorite, which is natural minerals. Okay, Atringite can also be called AFT or trisulfate. Okay, 3 parts of sulfate. Okay, and monosulfate aluminate can also be called monosulfate or AFM. The most commonly used name is AFM because it is short. AFT for Atringite or and CSH for calcium silicate hydrate. All right. And here shows compressive strength development of different compounds, C3S, C2S, and C3A with gypsum. As you can see from the figure, C3A will react instantaneously. Okay, in the first few hours, it will almost fully react. But the strength of C3A is much lower compared with the hydration product of C3S and C2S because the product of C3A, Atringite, and the monosulfate aluminate are much weaker compared to the hydration product of C3S and the C2S, which is CSH and calcium hydroxide. So the final strength of concrete is determined by the percentage of C2S and the C3S. Okay. Now, the difference between C3S and C2S is, again, C3S will react much faster, as we can see from here. It will achieve around 60% of its strength in the first week also, less than first week. But for C2S, it will continue to increase its strength after several months. So for higher early strengths, we should increase C3S. Okay. Now remember the key point. The rate of hydration, C3A is the fastest, C3S is second, C4AF third, and C2S is the slowest. And remember, CSH is the hydration product providing the strength of concrete, not Atringite, not AFM, and not calcium hydroxide. All right. So here shows different type of cement and how the temperature increase as well as the strength developed over 2 years of period. Let's look at the temperature. So type 3 cement is called high early strength cement. Okay, here. So the percentage of C3S in this example is 60%. Okay, because C3S will hydrate faster, as we can see from here. So type 3 cement will generate more heat and higher temperature. Type 1 cement is in the middle. And type 4 cement, which is low heat cement, will generate least amount of heat and lowest temperature because the percentage for C2S is higher, 50% compared to 25 for type 1 and 15% for type 3 cement. Okay, so again, the reason is because C2S will react slowly, so it will generate less amount of heat. Okay, so the percentage here is not fixed. Okay, for a certain type of cement, you only need to satisfy a range of percentage. Okay, for example, from 55 to 65% for type 3 cement for C3S. So remember, this percentage is not fixed. Depending on the cement producer, this percentage may be different. Okay. ESTM standard provide upper or lower limit for this percentage of compound. Okay. The figure on the right shows us the strength development. Okay, so type 1 cement is always in the middle, the green line, the blue line, always in the middle. For type 3 cement, it has higher early age strength up to around 1 to 3 months. Okay, but at later age, the strength will be catching up by type 1 and type 4 cement. Okay, for type 4 cement, for the first 1 to 3 months, it will have lower strength, but the strength will later catching on and be higher than type 1, type 3 cement. Okay, so the faster hydration speed will have higher early age strength, but final strength will be lower. Okay, the reason for that we're going to discuss in future lectures, but I will just tell you briefly. It is one of the major reasons because when we have faster hydration speed, the hydration product will be less homogeneous. As a result, the chance the concrete has certain type of flaw is higher. So that will somehow reduce the potential strength of concrete. Okay. So today you just need to remember type 3 cement has higher early age strength, but later on, its strength will be caught up by type 1, type 4 cement. Okay. Right. This is the ESTM standard limitation for different compound, for different type of cement. For example, this is maximum content for each phase. Okay, C3S, C2S, C3, and C4F. Type 4 cement, the C2S need to be less than 49%. Okay, but it is still much higher than the other type of cement. Okay, because C2S will react slower compared to C3S and C3A. Okay. The last column is called BF, or Boolean fineness. This is the surface area of the cement particles. The unit is square meter per kilogram. Okay. This is a measurement of the particle size. The higher the surface area, the smaller the particle size. Okay. Because type 3 cement is high early strength cement, to achieve the high early age strength, we need to increase the surface area or reduce the particle size. Okay, we can talk about that, why we need to reduce the particle size in future lectures. Okay. So let's look at closely the chemical reaction between the compound and water. Okay. During the process, the concrete transferring from fluid to a rigid structures, we have two important times: the initial set time and the final set time. Okay. The initial set time is the time at which the fresh concrete can no longer be properly handled and placed. So we need to mix the concrete, transport it to the job site, pour the concrete in the formwork, compact it, and finish the concrete before the initial set time. Okay, because after that, the concrete cannot properly handled and placed. Okay. For typical concrete, initial set time is between 2 to 4 hours. 2 to 4 hours. Final set time is defined as the time at which the hardening begins. That means the time we can detach the formwork from the concrete. So the concrete can stand on its own and workers can stand on the concrete. So concrete achieve enough strength at the final set time. Normally, 5 to 8 hours for final set time of concrete. Okay. So this is a short video talking about the hydration process of concrete.
This is a sketch of cement grains suspended in water. The solid hydration products form coatings around the particles of cement and gradually fill the space between. When the coatings first begin to impinge, setting occurs. There is a steady development of strength as the coatings grow together. The amount of strength attained by the mixture of cement and water depends on how effectively the space between the grains is filled up. Concrete will harden within a few hours, but hydration continues for weeks, even years after placement.
All right. So the hydration process of cement compound with water is very complicated. Okay. So here shows the heat of hydration for C3S, one of the major compound. Okay. So we can see here 5 different stages. Okay. The first stage is called rapid heat evolution, which is less than 15 minutes. So that's the process water dissolve cement grain into liquid form. So the cement can release the ions such as calcium and hydroxide ions into the water solution. The second stage is called dormant period. During this stage, not much happens. Okay, so that's the time is important for transfer the concrete from the cement concrete plant to the job site. So around 2 to 4 hours. At the end of this second stage, we have initial set time. So the concrete can no longer be handled. Okay. The third stage is called accelerating stage. Okay. So during this stage, we have more and more hydration product produced and more heat will be generated. The end of stage 3 is the final set time, which means the concrete can achieve enough strength, typically around 4,000 psi. 4,000 psi. And the fourth stage is called deceleration stage. Okay, the concrete can no longer be workable, but the strength will keep going up, but slower than stage 3. Okay. And the fifth stage is called steady state. Okay. The hydration is still going on even beyond the first months, but the rate of hydration is much slower compared to the early stages. Okay. So why we have these 5 totally different stages? The heat signature is quite different. Okay. So let's look at that process in details. So let me share the screen and draw some figures. Okay, so let's see. So this is a container, right? And we have, this is cement grain. All right, so this is cement particles, and this is water, liquid. Okay, so during the first stage, water will dissolve ions into the solution. So the major ions is calcium ions and hydroxide. and hydroxide ions. Okay, but the hydration product will not be produced until a certain concentration of these ions achieved. Okay, so until the concentration, this is the concentration of calcium and hydroxide ions, so achieve a so-called threshold concentration. So no hydration product or very little hydration product will be produced until this threshold concentration achieved. So that process will take around 2 to 4 hours. And that is at the beginning of initial set time. Okay. So again, until the threshold concentration of calcium and hydroxide ions achieve not much going up. That's the reason in the stage 2, we call that dormant period. Not much hydration product produced in the stage 2. So actually, stage 2 is the time when this concentration of ions keep going up until the threshold concentration reached at end of stage 2. So when stage 3 start, so the hydration will accelerate. We have more and more hydration product produced. Okay, so when we have hydration product produced, the hydration product will precipitate on the surface of this cement grain. Okay, so remember the 3 verbs. So dissolve. So dissolve means the water will dissolve ions from the cement grain. Okay. The second one is called diffuse. And the third one is called precipitate. Okay. So dissolve means dissolve ions, such as calcium and hydroxide. Precipitate means when the threshold concentration reached, hydration product will precipitate on the surface of cement grains. Okay, so the cement grain will become larger and larger. When the cement grain connect each other, the fluid will become a solid. So concrete start to get chiral strength. Okay, so precipitate of hydration product on the surface of cement grain. And diffuse means when we have more and more hydration product precipitate on the surface of cement grain, the ions is consumed. Okay, so the concentration level will going down. But remember, we need the concentration to be higher than threshold concentration, so the hydration product will be keep produced. So the water need to release more ions from the cement grain. So the water will penetrate into the layer of hydration product and release more ions into the solution. Okay, so these ions will diffuse through the hydration product, which is just generated. So this is what called diffusion process. Okay, and that's why stage 4 and stage 5 is diffusion control, depending on how fast the water can dissolve the ions from cement, and the ions diffuse through the layers of hydration product and get into the solution to produce more cement, more hydration product. Okay, so as you can see, the hydration process is very complicated, And this morning, I just upload a handout about hydration process of cement. Please read it after the class. Okay, so pay attention to these slides. You need to understand why we have these 5 different stages and try to understand what is threshold concentration. Remember, not much hydration product can be produced until the threshold concentration of the ions are achieved. Okay, so this is the important concept. All right, so this is a SEM picture of scanning electron microscope of hydration product. This is 8 hours. We can see in situ mass precipitation. That means the black color area is the cement grain. If you pay attention to the outside, you can see that it's needle-like hydration product, okay, generated around the cement grain. And also in the solution, we have more and more hydration product generated. So this is 9 hours. We have more hydration product. Okay. Right. This is close up of the hydration product on the surface of the cement grain. So this is a needle-like products such as CSH and ethylene form. Okay, that is how concrete change from liquid to a solid, and that's how concrete can achieve its strength over the time. Right. So again, we have 2 setting time: the initial set time and the final set time. We can easily measure the set time using the so-called VCAP needle. So it is named after the French chemist VCAP. Remember, that's the person who first invented the first artificial cement. So the French chemist VCAP. So we use a needle with a certain diameter and a certain weight, okay? And we prepare some mortar sample. Mortar is cement paste plus some sand. There's no coarse aggregate, no large stone in the sample. Okay, so we use the needle to penetrate the samples over the time. Okay, for example, after every 5 minutes, we penetrate and we record how much settlement the needle into the sample. Okay, and we can generate the curves when we connect all these data points. The initial set time is the time when the settlement achieved 1 inch or 25 millimeter. And the final set time is when the needle can no longer penetrate the sample. Okay, so very simple. The water-cement ratio, the water to cement ratio for the mass is 0.4. Okay. Here talk about cement fineness, or the particle size and the surface area of cement. It is last step in processing or grinding the clinker to produce cement. Okay, so we can measure the fineness use the surface area, so which is the total surface areas of 1 gram or 1 kilogram of cement particles. Okay. We can also measure the particle size distribution use other instruments such as laser. Okay. The most commonly used method is the Boolean fineness, BF. Remember, we talked about Boolean fineness in the earlier slides of today's lectures. It measures the air permeability, so we can get an estimate of the specific area of cement. For typical cement, it is 350 square meter per kilogram of cement. But for high early strength cement, we need to be 500 meter or higher. Okay. So let's talk about why we need higher surface areas or smaller particle size for high early strength cement. Okay, the reason is pretty simple. Okay, so remember the chemical reaction or the hydration happens between cement and water. Okay, so for the same amount of cement, so one has smaller size, another has larger size. Larger size. The surface area will be higher when the particle size is smaller. So that means the contact area between the water and cement grain will be higher. So that means we have more chemical reaction goes on between water and cement grain. So more water will make it easier for the water to dissolve the cement grain into the solution. So the hydration will be faster. So for type 3 cement or high early strength cement, we reduce the particle size. So we increase the surface area to make the hydration faster. Okay. All right. So lastly, let's look at special cement, such as blended cement. Okay. So we can blend Portland cement use some other materials such as steel blast furnace slag, okay, or some other type of pozzolans such as flash, okay, or silica film. We'll talk about these pozzolans in much more details in future lectures. But remember, the good things about blended cement is the heat of hydration will be lower. Okay, durability may be higher because a so-called chemical reaction named pozzolanic reaction. Okay, the strength may also be increased, and we can also save energy. Okay, because slag and other type of pozzolans may coming from industrial waste. Okay, so replace Portland cement, which need a lot of energy to produce, with the waste materials, we can save the energy and also money. Okay, but the disadvantage of this cement is it requires better quality control because slag, flash, and silica film are basically waste materials. So the quality control for these are not as good as cement. And also the strength development of blended cement is slower because pozzolanic reaction. Okay, so this is pozzolanic reaction. It is reaction between siliceous materials. Okay, sometimes aluminum and siliceous materials itself has no cementing properties, but it can react with calcium hydroxide together with water to generate CSH. Okay. Remember, for reaction of C3S, one of the hydration product of CSH, which is strong and durable. The other one is calcium hydroxide, which is weaker and also soluble to water. Okay. So pozzolanic reaction means the pozzolans coming from slag or flash or silica film will react with this weak calcium hydroxide from cement hydration. Together with water, it will produce CSH again. So it transfer calcium hydroxide into CSH. So make the concrete stronger and more durable. Again, we'll talk about this in more details. All right, here are some specialty cement such as white cement, which actually get rid of C4AF because the ferrite is the compound giving the gray color of cement. Or calcium aluminum cement, which will be used in cold weather repair. expensive cement for special situations, and rapid set or high early strength cement. This is not a focus for this class, but just remember, beside these 5 different types of cement, we have some specialty cement as well. Okay, so this is some of the key idea for you to think about it. And this is the reading suggestions. So focus on the handout and also the lecture notes. Okay, so yeah, sorry, take some more time today. Any questions before we dismiss?